case there were some questions you didn't want recorded, but this one is. The question was for people who are not here and listening to it on the YouTube video. The question was about the next test. I will put it out there. I'll try to do it sometime this afternoon. I believe it's ready to go. I can't say that for sure because I do my test when we were on campus. I always did my test in WordPerfect because I love their equation editor. The one in Word is awful, and the one in WordPerfect is probably decades old, and it's still so much better than anything I've ever used in Microsoft Word. And I also like the idea, well, nobody else uses WordPerfect, so no one really has access to my test because they can't read it. But that was a secondary issue. I just like working in WordPerfect, and it has a fantastic, so many things about WordPerfect are so much better than Word, but the equation editor is one of the top ones. So when we went virtual, then I had to get everything either translated to Word or done in a PDF format. And I can't remember if the second test I had done that because we were on campus the first part of spring term, but not the second part. I don't remember if I adjusted the test 2, and got it into one of those formats. So that's why I'm a little hesitant to say how soon I can get it done for you. I'm pretty sure I can take a picture and get it into PDF format, and take a picture with our iPad, and there's an Adobe Scan app on that I can do it and get it into it. It's several steps long, but it will do it, and but it'll be sometime this afternoon at best before I get it done. But if it's already in that format, then sometime in afternoon it should be able to be out there. All right, any other questions, issues, concerns, problems? Okay, let me make sure nobody else is waiting. No, they're not, I can tell. So I have 2 marks in my book, and it doesn't really matter because they're both at the very beginning of this equation. So example, so my take is we're in chapter 2, first order differential equations, section 2.5, solutions by substitution, and we're on we've got this section to go and 2.6, and 2.6 is numerical solutions. We'll talk about one kind of archaic method, but it is a numerical method. There are others. Most of them involve computer usage, which is the way to go, but I don't have those packages, and I don't think you do either. But if you do have them, you can pick those up in a later chapter, but this is the one in this section. And anyway, but example 1 on page 73, which is where I have the Billy's book, the PDF version of the text that she sent me. Thank you very much. Let me see. You can't see this, but Melissa, you're in the way. I've got to move the block where you are. Yes. Now I can read the whole page here. All right. Here's example 1. Solve this differential equation. X squared plus y squared dx. I think we did cover this first part of it. Plus x squared minus xy dy is equal to 0. Now, that's set up just as if it's great for exact differential, okay? Except that when you take the partial of the m here with respect to y, you get 2y. You take the partial of n here with respect to x, and you get 2x minus y. Not the same, okay? Not the same. So obviously in this form you cannot do this. You cannot use exact techniques. Not yet, okay? What you can notice here is that in this term, x squared, the degree is 2. In this term, y squared, the degree is 2. In this term, x squared, the degree is 2. And in this term, xy, x to the first, y to the first, that degree is 2. So this is what this section is calling homogeneous. And I've had one student try to correct me every time and say homogeneous, whichever you want to call them. One student, I can't remember who it was. It wasn't you, was it, Billy? Pulled it up on
No, sir, it wasn't me.
Yeah, it must have been one last term. Pulled it up on a pronunciation thing, typed it in, and said the correct pronunciation is homogeneous. So homogeneous it is, but if you like homogeneous, go for it. Okay, so this is a homogeneous differential equation because every term has the same power. I see no reason to go through that deal that you have. All you have to do is look at the degree of every term, and it's 2. So we can either let y equal ux or x equal vy. Either one of those. They're choosing this one. I think we went this far, and from this we use the product rule to say dy is u dx plus x du. And then we put it in here, and that's, I think, where we left off last time. So I will go back to the whiteboard, and you get to watch my pathetic little finger writing. Okay, I'm going to try to move, you can't see this either, but I'm going to move this taskbar out of the way so I have more room to write. And I'll also move the whiteboard as far as I can, so I'll be able to write on as much of it as possible. Okay, that's about the maximum I can get out of it. You can't see the other taskbars that are in the way, but they're in the way on my screen, so I can't write there. So here's what we've got. The original equation was, I guess I'll go on and write it down, though I hate doing it. X squared plus y squared dx This is as much fun as watching paint dry, isn't it? That's a pretty ugly dx plus x squared minus xy dy is equal to 0. Everything's great to do this as a exact differential, except it's not an exact differential. Your test that we talked about showed that it wasn't. So the assumption we're going to use, and I'll write this down too so we'll have it in sight, is this one: y is equal to ux. And I think last time I actually wrote this with a let in front of it. Let y equal ux. Always follow a let by a then. Okay? Then dy, whoa, that's an ugly d. dy is equal to, and this is the thing we just talked about in the book, u dx plus x du. Product rule. That's a pretty ugly u. Pretty ugly, that doesn't make sense. Okay, now we plug, instead of y that you have here and here, we plug in ux. That's a pretty ugly x. Okay, instead of the dy that you have here, we plug this in. All right, so let's see what that gives us. And I think we already did this. So without straining too hard, I'm just going to write that down. X squared plus u squared x squared, because y squared is u squared x squared, and the dx is fine just as it is. So what we're doing is basically moving from y's to u's, okay, in the hopes that we can make this an exact differential. And that will be plus, and the x squared stays in x squared. And then when you multiply and the minus, don't forget that, okay. When you put instead of y, ux, this will be x squared u, or ux squared. I guess we're writing the u first. Okay. Everybody see what we're doing so far? Okay. Now the dy is now u dx plus x du. Ooh, ugly. All right. Now, the next step here is to get all the dx's together and all the du's together. Okay? So, these are all dx's here. The only things to be added to that would be this term here multiplied by that. Okay? So this is going to be quite an addition. So I'm going to try to do that in one step so I don't have to write any more with this than I have to. So the x squared stays x squared plus u squared x squared stays u squared x squared. That's a u, don't confuse it with a y. That's a 2, don't confuse it with a 3. U squared x squared. That's an x. I don't know what you would confuse that with. All right, now let's do our others in here. Plus, and we're doing the u in front. That looks so much like a y. Don't let me mess up. Okay, this would be a ux squared. Okay, and this would be a u squared x squared minus u squared x squared. Okay, and that would all be by your dx. Now, I hope y'all are doing this too and letting me know if I'm making any stupid mistakes. Okay, now your du's are strictly just this thing multiplied by that, which would be plus a x cubed. That is a 3 that time, minus a ux cubed seems suspicious, but I'll take its word for it, du. Now, oh, and I forgot to do an important step here. This is still equals 0. I was so busy substituting in, I forgot that. Now, hold on just a moment, if you will. Let me see if I can do this from here. Okay. You might say, what in the world is the guy doing now? Okay. My wife has been working at home too. She's a researcher, professor at UAB, and She works downstairs in the office and I'm upstairs in a bedroom. She tried to get me as far away from her as possible because I'm so loud and talk all the time. Sorry about that. But today she had to go into the office, but she was still here when I started class, and I think she's probably left by now. I should have checked before I opened the door. So she has me close the door. Let me see. Hold on. Well, hold on just a second. Okay, can you still? What's that?
Does your wife know Dr. Erdman?
What field is he in? Which area?
He's the same field as your wife. He does infectious disease.
Okay, do you know if he's adult or pediatric?
He's adult.
Okay, she's in pediatric infectious disease, but I bet you she knows him because she does do things with the adult side too sometimes. But I'm pretty sure it's a large department, so she may not know him personally, but I'm almost certain she probably knows him. I'll try to ask him. Erdman, you said, right?
Yes, sir.
Okay.
Wife was my chemistry teacher.
Oh, I see. Okay. Okay. We're down at, are you from Auburn or UAB?
UAB.
Oh, you're from UAB. Okay. So his wife's a chemistry professor there. Wow, nice.
So
Okay.
they're both Dr.
They're both Dr.
Erdman.
Erdman. Yeah, we're both Dr. Fowlers, so I know the feeling. Okay. All right. Well, then I will. Now, she is not an MD. She's a PhD. She's a, well, actually, it's a DRPH, Doctor in Public Health, but she's a epidemiologist and she works and studies. She does the statistical analysis and things like that of the diseases that they're working on, mostly CMV. Yeah.
More one-on-one with patients. So he's an MD.
Right. Okay. Yeah, that's what I was going to say. So there is another disconnect there. And if he is mostly, does he do a lot of research too, or is he mostly just a clinical doctor?
He's been doing a lot of research
Right.
because of COVID, but
Right.
normally I don't think he does as much.
Right. Right. Okay. Her field has been CMV, which is cytomegalovirus, which mostly affects, I mean, anyone can catch it, but it's not a problem for anyone except pregnant women. And if the baby gets it in utero, then there can be no issue or there can be pretty serious sequelae. So her, most of her career, she studied that one virus. So she's done influenza, uh, what is the RS or something, respiratory syncytial virus, and she's done a few others, and she's worked with the adult ID docs. She's worked with the maternity, people. So she's done a lot, some things around campus. But I'll check with her and see. Dr. Erdman, I'll try to remember that. All right, good deal. Okay, but they're trying to. They don't want people on campus that don't have to be on campus if they can work at home. But they do want them phasing back in, so she's trying to go in once a week, and she's got some presentation, I think, with Merck coming up that she has to finish her slides on or something, and she thought she might be able to do it better at work than at home today. So anyway, she's gone today, and she's gone already, so I can have the door open. Okay. All right. What a terrible distraction. Notice here in this first group of terms here, even though it doesn't look at it, that's a u squared x squared plus u squared x squared, and over here we had a minus u squared x squared, so these add to 0. Okay, those two get wiped out. Okay, so what we're left with is a lot simpler, and I'll just as soon not write it again if I can help it. Now we have a differential equation in x's and u's. Let's see if by chance that might be exact. Well, what's the test? You take the partial of our new m here with respect to u, and that would be, this has no u in it, so we don't worry with that. This would be x squared. Okay, so if it's all right with you, I'm just going to call this m sub u. Now that's not the same m you had before. That was the m and n that had x's and y's in them, but I didn't ever write that down, so I'll call this m sub u is equal to x squared. And over here, this is our new n, and n sub x, and y'all are familiar with the subscript notation, right? Uh-oh, SpaghettiOs. This is 3x squared minus 3x squared u. That doesn't look good, does it? I'm just going to write that as times 1 minus u. Now maybe I jumped the gun on this one. Nope. We don't get an exact differential equation, obviously. Okay. What they did is what I was doing here at the end. Let's sort of separate variables. Okay. In this first term here, so this is out. I'm to save the embarrassment of leaving this on here that we tried the wrong thing. I'm going to wipe that out because obviously it's not exact. But one thing you might note, if I was paying attention, is that this is now separable, because here you can factor out an x squared times 1 minus u, 1 plus u, dx. Always go for the easy, not the hard. Exact requires a lot more work usually than separation of variables. So I should have checked this first. And that's a plus. It's a hard, ugly one. And this is x cubed times 1 minus u. And look at that. That is indeed separable. Okay, equals 0. Now, here's how I'm going to do this. I don't think it's the same way the book did, but it's how I like to do it. Let's move this to the other side, and rather than subtracting it, I'm going to reverse the order of this subtraction here, which is the same thing. That is subtracting it. So that gives us a, I think I'll write it here, x squared times 1, I'm going to write it now as u plus 1. That's the same. Addition is commutative. Is equal to, oh wait, dx, sorry about that. Okay, is equal to, now moving this to the other side, does everybody see what I'm talking about? That subtracting it from both sides actually is reversing the order of this. So that's going to equal x cubed times u minus 1. And that's why I changed it to u plus 1 and the other ones, just they'd look more alike. And that would be your du. Was that a sleight of hand, or did you follow?
I understand the U and the 1, how that switched, but is the x cubed not negative because it got, like, transferred, basically,
Okay.
to the 1 minus u?
Okay. How I took care of the minus sign, because all these are factors, okay? So I only need the minus in one factor. I put the minus with this rather than the x cubed. And when you negate this, that becomes u minus 1 then. You see, again, that was a sleight of hand. we could have subtracted this term as is from both sides, and then that would be a minus. This would then be a 1 minus u, right? I take that minus sign here and not multiply it by the x cubed, but by this factor, and make that u minus 1. And Dawson is here, so let me get him in. That probably just restated what I already stated. Does that make it any clearer, or was that just as confusing? Okay.
That's what I thought it was.
Right.
I just wanted to make sense.
Okay. All right. Good deal. Okay. I had a French professor in college, and he said he had studied in France, and in the French, and I think all European universities, the professor is out in front just saying, you know, lecturing, and nobody's supposed to ask questions. They're just supposed to taking notes and stuff. But of course, Americans didn't know that, and they're always asking questions. So he said he would always pipe in, you know, and say, well, what did you mean by this? And the professor would look a little upset and say, oh, it's American again. And then would just repeat exactly what he said without clarifying it whatsoever, you know, and then keep on talking. So I was hoping I didn't do the same thing, just repeat exactly what I had said and not clarify it at all. So thank you for at least saying I did. Okay, so what we're going to do now is divide the u plus 1 on both sides. So I'm going to wipe it out here and move it down here, u plus 1, and now I've got all the u's on one side, and I'm similarly going to divide the x cubed on both sides, and now we got all the x's together. Separation of variables. But this, of course, is going to become a 1 up here, and this is just going to be an x down here. And I'm sorry about the sloppy writing, but it's just so hard to write this thing over and over again. So now we have 1 over x dx is equal to u minus 1 over u plus 1 du. Was that sleight of hand too tricky? And by the way, I forgot to say, Dawson, welcome to class, but we're on in chapter 2, first order differential equations, section 2.5, solutions by substitution, and we're working on example 1 where we left off last time. And another thing that was asked about, and I'm going to try to do before the day's over, is give you get the test ready so I can post it on Blackboard hopefully sometime this afternoon. Now I can't swear I'll get it done then, because one of the emails I got tied up with this morning was from the dean, who's wanting something done with the fall schedule, and up until now we haven't been able to touch it once we submitted it, and now it sounds like it's something urgent. So if that's not too bad, I may have time to do it. If it is too bad, I may not get it done. All right, but I'll try. Now, I know how to do this one. Integrate this, 1 over x dx. Okay, first, was my last series of smudges here understandable? Yay or nay? Okay, that sounds really definitive, huh? Okay, but this side is pretty obvious, right? How in the world are we going to do that kind of an integral? So let me go on and write them. I'll try to make it more readable. So on the left hand side we have a 1 over x that used to be x squared over x cubed, and that just becomes 1 over x dx, and I'm real happy with integrating that one. Not yet, but I'm going to. Oops, I started to put my plus back in there, and that's not what I want. I want to be a equal sign. Okay, now I'm just going to go on and put this one in here. Do you know any technique that you would use to try to solve that differential equation, of that integral? Okay, substitution I don't think is going to be helpful. If that was a binomial up here and a monomial up here and a binomial, no, I'm sorry, I said it backward. Binomial up here and a monomial down here, that would be doable. However, it's not. Now, here's the trick. When you have a rational expression here, especially where the degree of the numerator and the degree of the numerator is either greater than or equal to the degree of the denominator, we divide. So here we do division, and in this case we can do it by synthetic division, if you remember that from way back in your past. And in synthetic division, your divisor, which is u plus 1, you just make that a minus 1 here on the outside of the block. Now if you want to do it long division of polynomials, it's real easy too, and you can do it. And in the numerator, you write just the coefficients, and that would be 1 minus 1. This is a flash from the past, right? Skip a line, draw a line, bring down that 1, and now multiply. Minus 1 times 1 is minus 1, and then add, and you get a minus 2. Now, this minus 2 is your remainder. The 1 here represents just the number 1 because you've just decreased the power here from 1 to 0. So basically, what this tells you, that expression here can be written as 1, that's supposed to be a 1, that is about the ugliest 1 I've ever written in my life, okay? I don't know how that happened, okay? Okay, so this expression here can be written as 1 minus 2 over u plus 1. Do it with long division and I think you'll see the same answer. The quotient, 1, minus the remainder over the divisor, x plus or u plus 1, and that will be that. So that's the integral I'm going to put over here, except I'm going to go on and separate it into two integrals. First, the integral of du, which I can do without your help, I hope, okay, minus, I'll pull the 2 out and do the integral, that's supposed to be an integral sign, okay, of du over u plus 1. It's supposed to be a 1. Ones are having difficulties today. Okay. Was that a sleight of hand? Or do you see what I just did? Do you understand the division part?
Yes.
Okay. And that's what you got in your division. And this is what it turns out to. Now let me make sure I haven't made a dumb mistake. They kept it with the 1 minus u rather than u minus 1. So I'm doing it slightly differently from the way the book did. But I think it's all going to come out in the wash, so we'll see. Okay? What's this integral? I think we all know it, don't we? 1 over x dx. Log of absolute value x, right? Now we'll wait and put all our constants together, so don't worry with them yet, okay? And then I hope you know this one, don't you? Integral of du is just u. Don't be saying things to me. Okay. Minus 2, and what's the integral or antiderivative of du over u plus? Oh! I did not have the button pressed, and it just decided to draw a line there. Okay. I haven't quite figured out this whiteboard yet. Okay.
Natural log of u plus 1.
Absolutely. Natural log of u plus 1. but you put that in absolute value bars because you can't take the natural log of negative numbers. Okay. And now if you want to, you can put your constant. Now because we got so many logs here, I think I'm going to make this constant log C. That is a constant, right? C is a constant, log C is a constant. And I'm just going to require that C to be positive. Okay? I can do it. It's my constant. Okay? So log C could be positive or negative because a log can be positive or negative. It's just that C has got to be positive. Okay. Now, what I do next is another sleight of hand. I want to, okay, that U is just U, so I'm just going to write it down. I'm running out of room at the bottom, so I'm going to come up here. I'm swapping sides here, okay. U is equal to, okay, the log X is over there, and that is absolute value. And I'm going to add this there, but I'm not going to quite add it like this. I'm going to add it as, am I going to add it or subtract it? It doesn't matter, okay? I guess I'll add it. Maybe it'll make it easier. As log of now. No, I'm going to write it as a subtraction, okay? Indecisive this morning, okay? Okay. Going to leave the subtraction there and make this U plus 1 squared. Now, do you see why I did that? I lost the absolute value bars because this thing's going to square it. Doesn't matter if it's positive or negative. When you square it, it's going to be positive. And that's one reason I decided to leave this. I could have left the plus here and does it to a -2. That would still guarantee it's positive, but it now would be in the denominator, which is where it's going to wind up going anyway. Okay, and then plus log C, because I chose to leave the constant as a log. Whoa, that's an ugly N. Now, using another rule of logarithms, this one was that you take a coefficient and move it up here and make it a power. That's what we did here. What we're going to do here is multiply. So U is equal to the log of, I'll put this in absolute value, at least the numerator part, because the C is still there, CX, because you can, the sum of two logs is the log of their product. I don't know if you remember that, but that's one of the rules of logarithm. And when the difference of two logs is the quotient of their product. So the CX divided by U squared, if I could get it to write, U plus 1 squared. Now don't have to put the absolute value there because you're squaring it. Okay. Now, can you guess what I might do next? It's not the proper use of the word, but I'm going to E both sides, okay? Makes this the exponential of U and the exponential of the log. The reason I do that, I'm going to come over here and write it, that's E to the U, that's okay, is equal to E of log. That undoes it. Those are inverse functions of each other. So what we have here is CX over U plus 1 squared, if I could read my writing. U plus 1 squared. Okay. My C is now embedded in here, so that's okay. And now finally, since the original problem was in x's and y's, I'm going to get it back in x and y. Remember here now, since Dawson came into class, he's got messed everything up here. You could probably see this. Y is equal to u times x. That was our original substitution. So instead of u, that implies that u is equal to y over x, right? So now everywhere we have a u, we put a y over x. So this becomes e to the y over x power is equal to cx over y over x, this is ugly writing, plus 1 squared. Okay, if I can get my pen to work. Okay. All right, I'm going to fiddle with that denominator for just a little bit here, and I'm going to rewrite this as x plus y, or y plus x, all over x. Okay, you agree with that? Least common, yeah, okay, so that denominator is going to be that, and then we're going to square that. So that puts an x squared in the denominator of the denominator, which moves it up to the numerator. So if you can allow me to do that in one step, that's going to give you a cx cubed, ooh, that's an ugly 3, over x plus y squared. Now, that is a solution. Not a particularly lovely solution or a pleasant looking solution, but it is a solution. Now, how they write it in the book, because they didn't do some of the changes we did, they have the x plus y squared over on this side, and then on this side they multiplied, let's see, let me see what they did. I don't know what they did. Seems like I have two extra x's in there they don't have. And right now I can't rectify those. And I'm a little lost of it's going to be close to impossible to go back and find where that happened. It may be, I don't think it could be, but it may be these are exactly the same representations, but I just don't see how. I know the C's are different, so it's a constant, but I cannot adjust for that. Sorry about this. I don't see where the mistake happened. Let me just check again. This u plus 1 was y over x plus 1 squared. That would be y plus x over x. Square that, y plus 1, x plus y squared. That works out. And that gives you an x squared down here. Maybe that's where I made my mistake. When I flipped it, I multiplied. I think that's correct though. If I had divided, that would give me, that would be perfect, I think. 1 over 1 over x is x. So 1 over 1 over x squared should be x squared. So sorry folks, I'd say go back and look at the book and do it. We came so close, missed it by that much. Okay, but I thought the way they were doing it was fairly convoluted, but evidently I was the one convoluted here. And I just don't see it. Okay. So rather than spend the rest of the class period trying to figure it out, follow the way they did it in the book. You'll see a lot of the steps are similar, but I don't see how it happened now. It says, although either of the indicated substitutions can be used in every homogeneous differential equation, in practice we try x equal vy whenever the function m of xy is simpler than n of xy. In these two, it didn't matter. The m and n were about equal simplicity. I don't see one any better than the other. They would do that. If this one turned out being a lot simpler than that, then they say do your x equal vy. Okay. Otherwise, y is equal to vx. Wait, I said it wrong. Y is equal to ux is the one they usually use. Okay. Now that's the one way to deal. That's a substitution to get a homogeneous equation into usually separation of variables, which was what we had and should have been easier to do, and I thought everything was pretty straightforward until I got to the end here. Let me just back up and see an earlier step if I can find anything. This step right here, they have log of x, which is what I have, is equal to u, and if you move the u to the other side, that works, plus, and they have a plus here, I had a minus, 2, no, that's on the same side with the u, so yeah, that's still correct, plus the log of our constant. So we're absolutely in agreement there. Okay, now what I did was everything. Well, I rewrote this, and let me make sure that didn't come out badly. U, that's this u here, is equal to log of I think that's where it did mess up. Where I said this was, I don't think it should matter, but this should be a minus, I think here. U is equal to, because if this was a plus log C here, when it goes and joins here, it becomes a minus log C. I see where I made my mistake. Okay, so I will take away what I just said I was not going to do. I'm going to do it now. Hopefully it won't be too bad. Okay, let's wipe this out. Okay, it's not a major change, but I think I see where the error occurred. Okay, it was when I was trying to avoid writing and skipping too many steps. Sorry about that. Okay, now, okay, this u I'm moving to the left and everything else to the right. Okay, and that's, I should have done it more carefully. This is u then is equal to See, this becomes a minus log x because I'm moving it. No, it stays positive. Sorry about that. This becomes a minus, but this becomes positive when I move it to the other side. So the log c, okay, another sleight of hand here. We could have made this a minus log c. It doesn't matter. So that's not the issue. So what we have here is the log. See, all those are logs, and we can make this a minus if we wanted to because it's a constant, okay? So that's going to be c times x times, and this is u plus 1 squared. Because when you move this to the other side, that becomes a plus. So I had it in the denominator. So what we have is your c, x, and then u plus 1 squared. That's where I made my mistake. That minus sign going to the other side, I messed it up. Corbin's here. Let me get Corbin marked here. Okay. Okay, Corbin, if you can hear me yet, I don't know if you can or not. If you can, we're in Chapter 2, First Order Differential Equations, 2.5, Solutions by Substitution. Still working on Example 1. I found out I made a really dumb mistake when I was doing it the first time. I messed up a sign, of course, and this becomes a square. Now at this point, we e everything, okay? And this whole thing here is what your log of, okay? So this becomes e to the u, and I think I'll go on and write in what u is. That's e to the y over x. You'll have to go back and follow our whole pattern here. Our substitution was y is equal to ux, and then dy is this, and we went through that whole spiel. Now I'm going backward, and since we have a u, if y is equal to ux, u is equal to y over x. So there's the left-hand side. It's equal to, and the e to the log, everything wipes out there, and here we have cx, and here is where you have the y over x plus 1, that's supposed to be a 1, squared. Okay, now I'll do what I said before, put this over least common denominator of x. You have y plus x over x, but it's squared, okay? So this would then be cx, okay? No, back off. Okay, get it again. Don't go too fast. You have an x squared in the denominator here. When you write this as y plus x, or x plus y over x. Square that, you have x plus y squared over x squared. X over x squared is 1 over x squared. So you have x plus y squared over x. Now, that's the form I have it in. That's the C there. It's pretty ugly. Okay, let's see if we can rectify what they did. Yes, what they did is leave this on this side, x plus y squared, and then multiply both sides by x, and they divide by c, but guess what? Their c was different from mine. Where mine is a c, theirs is a 1 over c. That does give us the correct answer. X plus y, pretty ugly here, squared. Now, why they chose to write it in this form, I'm not sure, but they did. They moved this to the other side, multiply both sides by no, I'm sorry, left this alone, divided by c, which is a constant, so it's just going to be a constant c, and then you have an x e to the y over x. And that's what they got. Sorry about that. So we did, I see where my error was. That minus sign right there, I didn't change it when I moved it to the other side. Did you follow that? Okay, sorry about the error there. Now, I'm sure he's still, yeah, I see Corbin is out there somewhere, but I can't see his name completely, but I see he's there. All right, any questions? I know that was confusing, but hopefully you got it done. Now, we've been going an hour and I have 45 minutes left, right? We go to 10, no, an hour and 15 minutes. Let's go a little longer, okay, before we take a break. Let's move to the next type of a substitution we'll do, and that's called a Bernoulli, to get it into the form of a Bernoulli equation. So let's scoot on down here. See, there's the answer they got, and ours wound up being in that form once I corrected my error here. And there's where they talk about, although either substitution can be used, remember the substitutions are y is equal to ux, that's the one we use, or x equal vy. Usually they use the first, but if the m of xy is a much, simpler expression than n of xy, in other words, the coefficient of the first is simpler than the coefficient of the second, then use x equal vy. And it could also happen that after using one substitution, you may encounter integrals that are either difficult or completely impossible to evaluate in closed form. Then try switching the substitution. If it's a homogeneous differential equation, that should work. Okay. Now what if it's not? And here we have another equation, and this is a Bernoulli equation. Now, I don't think we've run into this name before, but you probably have in other courses. Okay. Bernoulli is quite a name in, I don't want to quite say antiquity, but the early years of calculus and all else, there was a whole family of brilliant Bernoullis. Okay, there was a Johann, and his brother was Jacob. Okay, I think they both started with J. I think those were the two names, Johann and Jacob. They both had children, and some of their sons were brilliant mathematicians and physicists. In physics, you'll probably run into the Bernoulli effect, which is a very interesting thing. That was Daniel Bernoulli, one of the sons of one of the fathers. Okay, Johann and Jacob evidently were very competitive. One of them tended to be slightly sharper than the other one, but they were both awfully sharp, and the one liked beating the other mercilessly in competitions and stuff. So I think the very bright one also had a very bright son, and there was some sort of big math competition going on, and he knew he had it knocked because he just about always won it when they had those. He entered it, and he got beat by another Bernoulli. He could not believe his brother beat him until he found out it was his son had secretly entered the competition and beat the dad. And the dad, being so proud of his son, he kicked him out of the house. You know, that's how competitive and sort of dysfunctional that family was. But they were brilliant, brilliant mathematicians. Okay, I don't know if you remember L'Hopital's rule in Cal 2, I believe it was. L'Hopital got it from Bernoulli. L'Hopital was a student of one of the Bernoullis, and he acknowledged that he got it directly when he wrote his math book. See, what L'Hopital did, he wrote one of the earliest calculus texts, really a wonderful text. And because he wrote it, even though he acknowledged to the hilt that it came from whichever Bernoulli it was, I think it was Johann, he acknowledged them, everybody called it Bernoulli's, L'Hopital's rule, not Bernoulli's rule. And you think about someone who was so egotistical like Bernoulli, he got incredibly upset, but he had to admit that L'Hopital did everything right. It's just the whole math community, maybe to get back at this obnoxious Bernoulli, called it L'Hopital's rule, not Bernoulli's rule. I don't know. Anyway, there's a whole set of people you could write on there. Any Bernoulli, any L'Hopital, how Bernoulli came up with this equation, whatever. But please, folks, don't forget about your research paper. Okay, that was a paid commercial there. Here's a differential equation. dy dx is equal to p of xy. Oh, that's looking familiar, isn't it? Plus p of xy. But this time it's equal to f of x, which we've seen before. But now they put a y to the n out here. Without that y to the n, that's a perfect setup for a linear equation. But no, they had to put a y to the n here. Now if that n is anything, even 1, then it messes up everything. So you can't use a linear technique here. But Bernoulli came up with a way that you could, where n is any real number, not just integer, any real number. Now, of course, if n is 0, that's a linear equation. Okay, so when they say any real number, they really should say anyone other than n equals 0. Okay, 0 is a real number. If n was equal to 0, that's a linear form. But this is called Bernoulli's equation. And here they say it. Note that for n equals 0 and n equal 1, they say this is linear. Now, I was about to say that. Oh, yeah. If n is equal to 1 here, then you divide by y. That wipes out the y here, but it puts a 1 over y here. Then switch your f and your p, okay? And then this would be the term, multiply again by y, or an easier way to do that. If n is equal to 1, then your p of x becomes p of x minus f of x. Move the y over here, and then you have equals 0 here. That's a linear equation. So n equals 0 or n equal 1, that's a linear form. But for any n not equal 0 or not equal 1, so anything between 0 and 1, negative, beyond 1, whatever, here's the substitution you use. Let u equal y to the 1 minus n. And that reduces this form to a linear equation. So don't do it if n's equal to 0 or n's equal to 1, but any other n, positive, negative, fraction, decimal, rational, irrational, it doesn't matter. We're not going to deal with any complex with imaginary components, but we'll do anything else except n equals 0 and 1. Those are already linear. So let's see if we can do this. There's our substitution. U is equal to y to the 1 minus n. All right, here's the equation. X dy dx plus y is equal to x squared y squared. Okay, I think I'll go to the whiteboard and see if I can screw that up again. Okay, I'm sorry, see if I can work this out that way. Okay, does anyone need this mess there any longer? Corbin, did you get whatever you needed? I know it's messy. Okay, I hope that's a yes. So I'm going to clear it out of the way. Okay. Now, let me write down that equation again. Dy dx, I'm on the wrong page. X dy dx know if it's as painful for you to watch me write as it is for me to write, but it's painful. Plus y is equal to x squared y squared. Now, time out. This is an initial value problem, so we'll deal with it. Is this in a form we can deal with? No, we need to make a little bit of an adjustment. What that adjustment is, we want this coefficient to be 1, not x. Now, if this coefficient was a y, we may be in trouble. In this case, no, probably not. But we don't, with it being a function of x, yeah, we can deal with that. We're going to divide everything on both sides by x. Divide this by x, divide this by x, and divide this by x. And to divide that by x, I'm just going to lose the exponent there. Is that okay? That'll keep it from being quite as messy. It's already messy enough. Okay, so this new form is dy dx, which is just what we want. Now, whenever you do something like that, you really should stop and check yourself. Okay? Because I just divided by a variable, x, that x had better not equal 0. Well, guess what? If that x was equal to 0, you don't even have a differential equation, because that would have been 0 times dy dx. It'd be 0 plus y is equal to x is equal to 0. So there, the only solution to that, if x was 0, y has to be 0. So that's just the point at the origin. So I'm pretty confident that we can divide by x, okay, because that we didn't lose anything important. But here we do have, I'm going to write it this way, 1 over x, because that's going to be my p of x that we just did, remember? Times y, and that's exactly what we want here, p of x times y is equal to, and this will be x y squared. So here the n is 2. This is not a linear form. You cannot get that into a linear form by manipulating the y's. That won't work. Okay? But using Bernoulli's equation, or Bernoulli's technique, I guess you would say, here's your substitution. Let u, from what we just had, let u equal y to the 1 minus n. Let u equal y to the 1 minus n. Now, that seems simple enough, except you got to get y's to become u's. Now, the n here is 2, so let's clean that up a little bit and make it just y to the 1 minus 2 would be minus 1. Okay, well that's okay, but that's not really very usable here. This implies if u is equal to y to the minus 1, in other words, u is equal to 1 over y, then y is equal to 1 over u, or u to the minus 1, right? Now, of course, this means y can't be 0 either, but of course y equals 0, we've already talked about that. This just gives you x equals 0. That's no big issue there, okay? So, as before, anytime you have a let here, which actually your let was here, but it leads to this, then dy, and you could do this one of a couple of ways, let's call this dy dx, because that's what we want to substitute. That's supposed to be an x. I said x, and for some reason the stupid pen wrote y, and I don't know why it did that, but anyway, oops, wiped out everything. Okay, let's see if we can get that to work. Now, this may not be the best way to approach it, but this is how I would say. Dy dx is the same as dy du I don't think that's the way we want to go. You know, it is. Dy du times du dx. Yeah, that's the way we want to go. I'm sorry, I had a brain clog there for a moment. Okay. Now, what is that? Well, dy du is dy dx, because that's what we have to put it in here. That's why we wanted to go this way. Again, this is so painful for me to write. It has to be painful for you to watch. Okay, what's dy du? That's minus 1 times u to the minus 2. So it's minus 1 over u squared. I'm just going to write it u to the minus 2. I think I'm going to like that better. Minus u to the minus 2. Okay. So I don't need the underline here, but I bet you it's going to erase everything else that I wanted. Okay. Except what I want to erase. Okay. Okay. Let's do that again. It's equal to a minus u to the minus 2 times du dx. Now, we do want the du dx in here because that's going to be what goes here. All right. So let's write what we've got now. Dy dx is minus u squared, or u to the minus 2. Maybe I should put that over u squared. It doesn't matter. Du dx plus 1 over x, that's our p of x so far, y, oops, we don't want y, sorry, we're substituting for y. Y is u to the minus 1. So that would be 1 over xu. That puts it downstairs here. Okay? This is sort of messy, isn't it? Okay? Is equal to x times y squared. Well, if y squared would then be u to the minus 2, so I'm going to put it down here over u squared. Okay. Now, what we're going to do now, we're back to where we started with. We want this coefficient, the coefficient of your derivative term, to be 1. So what we're going to have to do is multiply by u squared, the minus u squared. Okay? So the multiplied by minus u squared is going to wipe out this. So you have du dx, that's a u, it's an ugly u, dx, that d is worse, okay, plus, no, minus, because we're multiplying by minus u squared, remember? That moves the u back up top, so now we have 1 over x times u. Surprise, surprise. Almost the same form we had before. And that's equal to, guess what? Multiplying by minus u squared here is going to wipe out the u squared here, and you have a minus x here. There is our new differential equation. That differential equation can be solved. That's a linear differential equation. Now let's just see if it might also be separable. I don't think so. Okay, so I think we are going to have to do our linear form. And of course we remember our linear form. Our p of x now is minus 1 over x. Okay, that's your p of x. What you do with the p of x, you take the you integrate it. So the integral, I'm going to put the minus out front, minus, if I could get the pen to write, all the time it writes when I don't want to, okay, minus 1 over x dx and of course what's that integral? Help me somebody. It's minus log x, right? Or log x to the minus 1, or log of 1 over x if you prefer that. What do we do that with that integral? We e it, okay? Ooh, that's an ugly e. And that just gives you 1 over x. That's now our integrating factor. E to the integral log x. That's it, 1 over x. So what we do with that, I wish I had more room. I think I'll write it over here. This will be 1 over x du dx. Remember that is a u, it's an ugly u. Okay. Whew. Okay. And then this becomes a minus 1 over x squared. So I'm going to write that, I think it's x to the minus 2. Probably shouldn't, but that's okay. U is equal to, and when I multiply 1 over x times a minus x, I get simply a minus 1. Okay. Now, that u substitution, integrating constant, okay, that should have made this side a perfect derivative. A d by dx of that integrating factor, x to the minus 1 times y, or u, I'm sorry, not y, u. That should be what it becomes. Let's see if that's true. Let's take the derivative of u with respect to this. So that's the first, which is 1 over x times du dx. Yes, that's right. Plus the second, u times the root of the first, minus x to the minus 2. That's exactly what we've got here. Okay? So this is equal to minus 1. Well, now, let's write it in differential form, put the dx over here, and integrate both sides. Well, the integral of a derivative or derivative of an integral is just the argument. So this will be, I'm going to write it this time, is u over x is equal to minus x. Whoops, that's ugly. Okay, and here we can put our plus c in here. This is where we put our constant in, multiply both sides by x, and you have u is equal to, I think I'll come over here and write this, u is equal to minus x squared plus cx probably should have started with that. Cx minus x squared. And then write what u is. There it is. U is equal to 1 over y. So this will be 1 over y is equal to minus x squared plus cx. Now I'm going to change things around a bit and write this as y is equal to 1 over cx minus x squared. Now I hope that's the answer they get in the book. Let's see. Well, they keep the minus in front, but y is equal to 1 over minus x squared plus cx. Exactly. I don't know why they didn't write the other way, but they didn't. Okay? So that's a Bernoulli's equation, and that's how we solve it. The substitution there is, and again, differential equations is a series of tricks. If the trick works, call it a method. This is what Bernoulli, the trick he found, and we'll call it a method. All right, any questions on that? We got the same answer in the book. They wrote it slightly differently, but we got the same answer. So let's now move back to the book. And there we are. All right, now, if you don't mind, we have, 45 minutes to go. I need a bladder break. All right, to do one. Okay, we finished here. There's the answer they got. Y is equal to 1 over minus x squared plus cx. I said tx minus x squared. Now we're going to do another technique, and this is a reduction, another reduction. So let me pause the recording here. And I don't know where, there it is. Okay, so here's the last technique we're going to do, reduction to a separation of variables. Now here's a differential equation form that we are going to be dealing with now. dy dx is equal to some function of x and y, but it's a linear function of x and y. You might say, let's see, it's a function of a linear grouping of x and y, f of ax plus by plus c. That, they claim, can always be reduced to an equation with separable variables by means of the substitution, let u equal this thing right in here, okay, ax plus by plus c. Now, the requirement here, b can't be 0. Well, guess what? If b is equal to 0, then you already have something that's separational by, you have a function of x only, okay? So then just do your dx over here and integrate. So, but if that b is not 0 and you do have a term there that you can't separate because it's plus in there, not a multiplication, then this is the technique. So here's what we've got. An initial value problem this time. That doesn't make any difference. You still do it the same. Let's go to the whiteboard again and work this one out. Okay. All right for me to erase this scratch. Sort of proud of it. I didn't make any stupid mistakes that I could detect. Okay. So let's clear it out anyway. And here's your problem. The dy dx linear, well, not linear, first order differential equation, dy dx is equal to minus 2x plus y squared minus 7. Okay, initial condition of when y is equal to 0, when x is equal to 0, y is equal to 0. Okay, time out, folks. Wait a minute, I thought the dy dx is supposed to be a function of some linear combination of x and y. Well, this would be a combination of x and y, and it's some function of that. You square that combination and then subtract 7 from it. Yeah, that's a function of a linear combination. In this case, our c is 0. Well, that's okay. That's perfectly all right. So basically what we do, our substitution is let u equal to that linear expression. Okay, so it'd be a minus 2x plus y. The only requirement is b is not 0. It's not, it's 1. There is our substitution. Always when you have a let, follow it by then. And what's your then here? Du, okay, now your independent variable here is x. So this is a du dx, okay? So that's going to be a chain rule situation here, implicit chain rule situation. It's going to be your innermost part twice the innermost parts. That would be 2 times a minus 2x plus y to the first power, okay, times derivative of the inner part, which is a minus 2. You're taking the derivative with respect to x, plus dy dx. I'm only writing that way because that's what we've got. Okay? If that's your u, the du dx, remember, is, and by the way, I probably should put, in fact, let me just write it this way, du dx. That's much better to write it this way, I think. Most of the time we write it in differential form. I think this way it's better to write in derivative form. Du dx is, I'm sorry, I'm doing the wrong thing. Okay, let's start that over again. I was taking the derivative of the whole thing. That's not what we got. Just derivative of this with respect to x. So now I think I will go back and write it the way I meant to the first time. Okay. Sorry about this. Okay. Du is equal to minus 2 dx. Because this is du dx. Okay. But plus dy dx. So now I think I will go back and write it the other way. I think I will. That's right, this is du dx. That's what we want anyway, du dx, and this will just be a minus 2. Sorry I'm so indecisive this morning. I don't know what it is. It must be Thursday. Okay. Let's make sure that's right. If u is equal to 2 minus 2x plus y, du dx is then going to be minus 2 dx dx, which is 1, plus dy dx. Okay? So what we're going to do with this is write dy dx is equal to du dx, that's what we want, plus 2, right? Add 2 to both sides, and you get dy dx is equal to du dx plus 2. All right, now we go up here. Dy dx is this thing, so that's du dx, if I could get my pen to write, here we go, du dx plus 2 is equal to, and this is u, so that would be u squared minus 7, right? Well, we don't want du dx plus 2, we just want a du over here. So let's subtract 2 from both sides, and what do we have? Du dx is equal to u squared minus 9, because you subtracted 2 from both sides and got that. Now already I can see some alarms going off here, but let's see what's going to happen. Let's write that in differential form, and that's u squared minus 9. Well, I don't think any alarms will go off. This will be okay. Yeah, they are. They're still going off. Dx, but then we want to divide, this is where the alarms go off, u squared minus 9. Okay, so we'll divide this side by u squared minus 9. Dx is no longer there. I should have erased it. This is no longer there, so I'll just wipe this out. And now we can do separation of variables. Or can we? Can you integrate this side with respect to u? Du over u squared minus 9. Now, right off the top, I want to say this. U cannot equal plus or minus 3. That's the alarms that are going off in my head. That cannot be plus or minus 3. So hang on to that concept. So may not enter the picture anywhere here, but we're going to deal with it. Let's see up here. When x equals 0 and y is equal to 0, u is equal to 0. That's going to be okay then, okay? Because u is not plus or minus 3. So when I see this, I know that can't be. Let's make sure nothing up here. If this had given you an initial condition that made u equal plus or minus 3, the problem is ill-posed. You can't do it. This one's okay. So proceed. Yes?
So is this part right here, is this bit right here, is that the integral of, is that raised the dx? Or did you divide it?
Okay.
dx
Okay.
by,
Okay. Is that a u there or y? I know mine looks that. Is that a u?
that's a u,
Yeah, yeah. Okay, what I did with the dx here, I wrote it in differential form so I could integrate both sides. So the dx is no longer there. Okay, so that's not there. Huh?
I understand that.
Right. Here's how I'm going to adjust what you did. Okay. Is that okay? Because the dx is no longer there, it's over here.
These two are like multiplied together, so it becomes du over u squared minus 9.
Du over u squared minus 9. That's absolutely correct. And the integral over here is just simply an integral of dx. I can do that one. Okay. I want you to do the hard one. How are we going to do that one? Any guesses? Needed. What's that again?
Which one are you asking?
This one right here, your red one here with my adaptation on it. How are we going to do that integration? Anyone got an idea? Dawson, you'd better. I had you in Cal 2. Didn't I? I think so. Remember what technique? Not by parts. It almost sounds the same. Partial fractions. Remember that? What you do, you take the integral here, the integrand here, this part here. I'm going to take it up here and say, now the first thing I'm going to do is I'm going to factor it. Okay, u squared minus 9 is u plus 3 times u minus 3. Agreed? Okay. Now, I'm hoping that this can be written as some constant a over u plus 3 plus some other constant b times over u minus 3. Okay, in other words, this is a sum of two fractional forms. The coefficient of one is this, the coefficient of the other is that, and by least common denominator and stuff like this, we can make this work. Okay? Now, here's the trick. And it is a trick, and nothing but a trick. Okay? What we're going to do to this is multiply everything on both sides by this denominator. U plus 3 times u minus 3. So that's going to wipe out this denominator completely and leave just the number 1. Okay? Now when we multiply this term by u plus 3 times u minus 3, the u plus 3's are going to go out. Okay? And that'll just give me an a times u minus 3. Now I'm not writing everything down because it takes so long and is so painful. But do you see what I just did? Multiplied everything on both sides by this product here that wipes out the denominator here, leave me a 1. Multiplying this by this, the u plus 3's go out and you're just left with a times u minus 3. Right? Doing the same thing, multiplying this by that product, the u minus 3's are going to go out and leaves you a b times u plus 3. Okay, are y'all okay with that? I haven't written it down, but that's what I'm doing. Now here's the part that always makes my skin crawl. But it works, so you have to do it. Okay? What we're going to do is let u equal 3. Now that sounds innocent enough, doesn't it? Okay, let u equal 3. The left-hand side is still 1. The right-hand side becomes, this term goes to 0, right? 3 minus 3 is 0, and then 3 plus 3 is 6, so this is equal to 6b. Agreed? Which this implies that b is equal to 1 over 6. Agreed? Okay. Now, you might ask yourself, why does it make his skin crawl? Because look, if you let u equal 3, remember that's what we said at the very beginning. U can't be plus or minus 3, and yet we turned around and let u equal 3, but that gave us a value for b. And guess what? It works. Seems like it's unfair. It seems like it's violating everything, but it still works. So we'll do the next one. Let u equal -3. I can't write now. I got so excited about that. Let u equal -3. And if you do that one, the left-hand side is still 1. The right-hand side becomes -6 times a plus 0, because -3 plus 3 is 0. So this implies that I don't know how or why it happened, but everything Melissa wrote is gone now. So I just happen to look down and say, what happened to our integral here? I guess when I start, oh, you cleared yours. Okay. Okay. Yeah, okay. So we'll get it back in just a second. This implies that a is equal to -1/6. Okay. Oh man, I have a little bit of a pinched nerve, and sitting too long in one position makes my whole leg ache. So that's why I'm scrambling around a little bit trying to get that to quit aching. Here was my integral that we had before that Melissa erased on us. Okay, it was that u squared minus 9, 1 over u squared minus 9 du. I'm trying to think what that was there. Yeah, that's right. Yeah, so let me erase that part here because I don't think we need that here. Okay, u squared minus 9 du, and that's equal to integral of dx, which I can do the right hand side, so don't worry about that. Okay, now let's rewrite this integral, because the 1 over u minus 9, u squared minus 9, is now 1/6 over u minus 3 minus 1/6 times u plus 3 over, well, you know what I'm trying to say. So this side here, this integral here, I'm going to try to start writing it here. This is the integral of, I'm going to bring the 1/6 on the outside. Now I'm leading off with the b because it's positive, and that would be du over u minus 3, that was what the b was over, right? Minus 1/6, that was because the a was a negative, times the integral of du over u plus 3, because the a was over u plus 3. And this is equal to, I'm going to go on, well, let's go on and solve those integrals. What is this? That's 1/6. It's the antiderivative of du over u minus 3.
Natural log of the absolute value of n minus 3.
You got it. Okay, that should be a straight line there. U minus 3. It's ugly 3. Minus 1/6. The log, natural log of, you got it. It's supposed to be, that's a u. I'm sorry, I'm writing an x. Okay. All right. U plus 3. And that's equal to integral of x dx is just integral of dx is just x. And we could put our plus c here, but I'm wondering now if perhaps we should make it log c. Let me see if which way they write it. Do they do? No, they just, well, they ultimately will do that. Okay, I'm going to write it as a log c, just to keep from having to make so many c substitutions. Log c. Okay, now what I'm going to do here, and I think I'll go up, if you don't mind, and erase something up here that I think we've already used and we won't need it again, and it's taking up white space that I need. I think that might be enough. Okay, and here's what I'm going to do. This is the same as log of this thing to the 1/6 power, right? So this will be the log, natural log of, I'll keep the absolute value bars for now, u minus 3 to the 1/6 power. I'm regretting I did this now. And yuck, should have looked ahead. Do the same thing here. The natural log of absolute value u plus 3 to the 1/6 power. Okay, and that's equal to x plus log c. It's just a constant. You can name it anything you want to. Okay, what this is also the natural log. Probably am going to need more room. Natural log of u minus 3, that's supposed to be a 3, over u plus 3, because the minus puts it in the denominator, and the whole thing, absolute value to the 1/6 power. And that's equal to x plus log c. Okay. If you don't mind, I know I do this all the time, let's not make that a plus log c, but let's make it a minus log c. Okay? Okay? It's a constant. It can be plus or minus. It doesn't matter. But I want it a minus log c because I'm now going to add it to the other side. And when I add it to the other side, then I can make, I'm doing two steps at once here. This would make the x equal to c times, no, yeah, I'm sorry. The log of c times the absolute value of u minus 3 over u plus 3 to the 1/6 power. Now, why would I want to do that? So I can e both sides, okay? Oh man, my leg is getting stiff. So if I e both sides, that gives me an e to the x. I'm going to reverse sides again here. So this will give me a e to the x is equal to, when I e to the other side, it's c times this thing here, u minus 3 over u plus 3 to the 1/6 power is equal to e to the x. All right. Now, I do want to mess around a little bit with the C again. Sorry about that. If I'd have been looking ahead, I would have got it. Okay. Okay. But what I want to do is raise both sides to the 6th power. Okay. Now I think I'm going to have to erase some more. So let me come up here and do some more erasing. I think we can erase all this. It was fun while it lasted, but it don't need it anymore. Okay. All right. Now, raise both sides to the 6th power, but that means c to the 6th, but that's still a constant. Okay. And what we will have then is u minus 3 over u plus 3. This is always so tedious to do this, but it's is equal to, now I raise the 6c to the 6th power, it's still a constant. I'm going to divide by that. It's still going to be a constant. So this is going to be a new c, a different c, but I'm going to write it just as if it's the same and make that as c e to the 6x, because I raised that to the 6th power. Now this is not the same c that we had here, but I moved it to the other. I raised it to the 6th power and divided and all that kind of stuff. It's just a constant. Okay. Now, what we're going to do now is I lost my absolute value bars, and they always seem to lose their absolute value bars. Okay. And I guess the reason is you raise it to the 6th power, and that's always going to be positive. I can't think of any other justification, but they did. But then what you do is multiply both sides of this equation, if I could find my pen, there it is, by u plus 3. Okay. Now I want to multiply everything out, and this will be a u minus 3. This is just algebra from this place on, and that will be c u e to the 6x minus, let's just pull the c on the outside, u e to the 6x minus 3 e to the 6x. I can't get the pen to write. There it goes. Okay, the c is multiplied by that. Okay. Well, sort of. I do want to, I didn't want to do that. Not looking far enough ahead. Let's go on and put the c in with the minus 3. Okay. Now, what we're going to do now is get the u's on one side and the non-u's on the other side. So this will be u I'm going to divide out 2. 1 minus C e to the 6x. When you subtract this from both sides and factor out the u, that's what you get there. And then I'm going to add the 3 to both sides and give you 3 times 1 minus C e to the 6x. Now I've done something wrong because one of these is supposed to be a plus and one's a minus. Let me see where my mistake was. The right hand side is supposed to be a plus. Oh yeah, that was a plus. I just couldn't read it. That is a plus. I read it as a minus. Okay, so that is a plus. I knew that couldn't be true. Okay, so now we've got what u is. U is equal to 3 times 1 plus C to e to the 6x over 1 minus C e to the 6x. All right. Oh man. All we do now is go back and plug in what u is. Okay? So I need to erase some more. Those operations there always take so much room to write. So let's get rid of most of this. Probably could get rid of more of it. Let's see if we can. Yeah, let's get rid of this too. No reason having that stuck in the middle. Okay. And why not go and get rid of this too? Hopefully you got it. This whiteboard does erase a lot faster than my old one did. That's the only advantage I see of it. But I could use a stylus on the other one. I can't on this one, so it aggravates me. Okay, so let's plug in what we got. Minus 2x plus y is equal to 3 times that mess. I'm not going to write all that mess again, but you know what it is. That mess right there. Okay, so solve for y, and you get y is equal to 2x plus 3 times all that mess. And this is all in terms of x. Now we put in our initial condition. When x equals 0, y is equal to 0. Okay? So what does that give us? 0 is equal to, the 2x goes to 0, 3 times 1 plus c, and when x is 0, 6x is 0, e to the 0 is 1, so it's 1 plus c over 1 minus c. Okay? Now, basically, 3 is not 0, so 1 plus c must be 0 for this side to equal that side. So that means C is equal to -1. So now we wrote our answer as, and this time I will write it all in there, y is equal to 2x plus 3 times, open parentheses, 1 minus e to the 6x over 1 plus e to the 6x. There's our answer, because the c was a -1. Let's see if that's what they got. 2x times 2x plus 3 times 1 minus e to the 6x over 1 plus e to the 6x. Fantastic. Now they put the parentheses in different places. I don't care. Okay. That gave us our solution. And we finished 2.5. You can now do any of the odds that are in the back of the book, 1 through 13. Do either 11 or 13 if it's there in the back of the book. Do any of the odds 15 to 19 if they're in the back of the book. Do 21 if it's in the back of the book. You can now do any of the odds 23 to 27 if they're in the back of the book, and 29 if it's in the back of the book. If you can see any of the odd discussions, you can certainly do those as well. Usually they're not, but you can take a look and see what they are if they're back there. Number 35, however, I'm going to bring to your attention because it introduces a differential equation known as Riccati's equation. Sounds like a good Italian dish, doesn't it? But anyway, if you want to write on that, who in the world was Riccati? What was his equation? Who uses it? Anything such as that, there's another potential paper topic. Another one is, and I think we mentioned this before, the logistic equation. That's in mathematical modeling. That's also used a lot in diseases. And you can take a look at that as well. And unfortunately, we only have 1 minute left. I don't think that's enough time to get started on numerical method 2.6. So definitely don't think you have to do. And by the way, Corbin, I said this earlier. I think we may have lost Billy. I don't know if we have or not, but Billy heard it. I'm going to try to put the test out there this afternoon if I can on chapter 2. There is at least one question, maybe two, that deals with numerical methods. Don't worry with those because we'll do those next Tuesday, but you can get started on the first. I can't remember how many questions there are. There's quite a few. It's a 2-pager, but I promise you there's not as bad a calculations as there were on the first test. But you're still going to have a bit of stuff to do, so you can get started on the second test if I can get it out there this afternoon. I was explaining before, I can't remember now if I have it in a form that you can access. If I don't, I've got to get it in PDF or something else. So stand by. It will be a 2-page test. It'll be posted under Blackboard message. But I've got several other things I've got to see how crucial they are to do this afternoon, so I may not get it out there this afternoon, but I'll give it a shot if I can. All right, any questions, concerns, problems? I just talked past 10:45. Any questions? All right, if not, have a good, safe weekend. Take care of yourself, and we'll see you on Tuesday. All righty. Thank you. I'm ending the recording, so see you then.